So we will complete the proof of the von Neumann theorem. This will take us a concrete part of the lecture of today. And then we start building quantum field theory by reconsidering before certain properties of the solution of the classical field equation that you probably know, but it is better to have very well on mind. So let me summarize the idea we discussed last week. The first is that we had described a separation between the objects that enter in a classical or in a quantum theory. We distinguished the algebra of the observables, things you can measure in your laboratory, and the states, omega, that provides the expectation value of the elements of the algebra of the observable. These are the outcomes of your experience. So we gave to this algebra a general mathematical structure which is called C-star algebra. I don't know if you tried to construct examples doing your homework. And let me repeat what are the properties of a C-star algebra. First of all, is a Banach space. Means that it is a vector space. That if you have two elements of the algebra, you can construct linear combination of elements of the algebra that do belong to the algebra. And it is complete with respect to a norm that you assign on it. So there is a norm which maps the algebra into the real numbers. And as a Banach space, the algebra is complete. You can take limit. And when you take the limit belongs to the algebra. Second, it is an algebra. So there is a product between the elements of the algebra. You take a pair, and you have their product. You can have in mind as a product the commutator of two operators. This is a product. And the product is continuous with respect to the norm, means that AB is less or equal than norm of A, norm of B. Third, there is a star operation that sends A to A star, which is an involution, A star star equal A. And fourth, the C-star property. How it works, this? It is electrically commanded. Do you know?
The thing in the middle, you have to press it. A few options.
I don't know how to work.
All over it. Yes. Okay, so, for example, this one tells you what's on the bottom. So this time, not this is the bottom.
Not really. Okay, that's better. Stop. Thanks. Thank you very much. And so the C-star property tells you that the norm of A star A equal the norm of A squared. So this is the characteristic property of C-star algebra. And if you remember the formula for the spectral radius of an operator that tells you that the spectral radius of A star A equal the sup of the lambda belonging to the spectrum of A star A equal to A, the norm of A star A, because A star A is a normal element, this relation tells you that because of this property, the norm you can put on a C-star algebra is essentially unique. So this is why C-star algebra are more restricted than Banach algebras. Okay? So this is the first notion. This describes the structure of the observables. And now the states, which describe the outcomes of experiments, are linear functional on the algebra, which satisfy the positivity property. And it is possible to show if you have that if you have a C-star algebra, a state exists. So the second point we were discussing last. So this is just a summary of the general structure of a classical or a quantum theory. And the second big thing we were discussing last week is the GNS construction. If you have an algebra, a C-star algebra, and if you have a state omega, there exists a Hilbert space H, a representation P of H of the element of the algebra into the bounded operators in the Hilbert space. So we can use this notation, or the standard notation also in book of quantum mechanics is to put a hat on the operator. A is an operator going from H to H. It is a representation in the sense that it preserves the algebraic structures, including the star operation. And there exists in H a unique, a cyclic vector, C of H, in such a way that the expectation value omega of A is the mean value in the state P of A of the representative of the element of the algebra. So this says that if you measures in your laboratory the quantity A, there is a Hilbert space interpretation of this measure. There is a state in a Hilbert space, and this measure is intended to be the mean value of the operator in the Hilbert space in the state. So this is need not be to be considered an axiom in quantum mechanics. It is a consequence of the C-star algebraic structure of the theory. And third, every other state, this representation is unique. Given omega, if you have a Hilbert space, a representation, and a cyclic vector, a second one, this is equivalent to this one. This is the content of the GNS construction. You yourself a state, you have a unique representation in a Hilbert space having a cyclic vector. So this is a summary of what we did last week, and then we are going to discuss the von Neumann theorem. Yes?
Is there a notion of a pure state at the algebraic level?
The pure states, so the mixed states are the states. If you have two states, a mixed state is a state which can be expressed this way, with lambda as a combination, as a convex combination of two other states. The pure states are those states who cannot.
So there's something slightly confusing to me. Omega here in the formula may not be pure, right? But in the GNS representation, it has become a pure state. In the sense that the expectation value of A in the representation is just one vector.
There is a cyclic, it is cyclic. I didn't say it is pure.
So psi omega is a pure state in the Hilbert space. It's a vector in the Hilbert space. It's not a density matrix.
I mean, give yourself this state. This state is not pure. you can do the GNS construction. So the GNS construction doesn't say that the state is pure.
In the Hilbert space representation?
In the Hilbert space representation, all vectors give states. But the fact that they are pure or not depends on if in the family of all the states, if they can be written as a convex combination of other two or not. It means if you have, this is the family of the states, let's say, the extremal elements are the pure states, and the convex combination are the mixed states that can be expressed indeed also. Maybe we come back on this point when we discuss the KMS representation, okay, more technically. But the GNS construction doesn't say that the state is pure. You can do a GNS construction in a thermal state, for instance. You see what I mean?
I see that, but in quantum mechanics, when you can write the expectation value of an observable by contracting it with two vectors, with a vector in a Hilbert space, this is a pure state. A pure state is a state that can be written as a vector, and a mixed state is one that needs a density matrix. So once I've done the GNS construct and I end up with this right-hand side here, what I see is the contraction of A, pi of A, in a pure state.
In a vector.
Which I would call a pure state in quantum mechanics.
The definition I can tell you is this one. Then there is a question concerning the irreducibility or not, the representation. So, question if you construct this way an irreducible representation or not. This will tell you if your GNS construction is pure or not.
So your psi omega doesn't have to be a vector in the Hilbert space?
Psi omega is a vector. It is not a pure state in this sense. And the question is if the representation is irreducible or not.
So
we can discuss this issue when we discuss...
so just to clarify, in the case where the representation is irreducible, the two definitions you mentioned are coincide?
They coincide.
Is this what you're saying?
Yes.
Okay. So
has to do with the irreducibility.
Okay, thank you.
Okay, so we want now to discuss one particular construction of a particular the particular Weyl algebra, which is supposed to describe one or maybe n particles quantum mechanics. Okay, so the general structure is that you start with a classical Hamiltonian system in which you have set up your Poisson brackets, and you promote this to commutation relation. This is the standard way of describing the situation in every book of quantum mechanics. Okay, so let me tell you that quantization comes in because of this I. This I is the key of the story. We will keep discussing the appearance of an I there. So these are in a way functions, and these are operators because of the I. So if you have two self-adjoint operators, the commutator is anti-Hermitian, and that's why you get an I here. So this way of describing the situation is not does not belong to this description, because as we were saying last week, it is not possible. Let me tell you. Let me put here QMP hat. So I'm meaning at this moment operators in a Hilbert space. Or if you want to represent this commutation relation in a Hilbert space, Q and P cannot be bounded, as we were discussing last week. I already gave an argument. I will give a second argument in a short while. So the idea, so the point is that if you want to set up a Stone-von-Neumann theorem at this level, and you give yourself only Hermitian operators, there is no uniqueness. There are plenty of inequivalent representation of this commutation rules. So we have to impose a restricted condition on this. And the idea, so this was already clear at the very beginning of quantum mechanics, and the idea to go around the difficulty, not to solve it, by the way, is the idea of Weil. Let us consider bounded function of these operators, which are the exponentials. So we define u of alpha a to the I alpha q and v beta equal to the a to the I beta p. Okay. So these are bounded functions of these possibly, probably unbounded operators. Okay. So I remove the hat here. We are talking at an algebraic level. So we have to set up the commutation relation for these operators. Okay. This is based on the maybe well-known Baker-Campbell-Hausdorff formula. If A commutator B equal C commutes with A and B, then this product of these two operators equal to this sum. Is everyone comfortable with this or not? Yes? No? Do you know the Baker-Campbell-Hausdorff formula?
Sorry?
You know this formula already or not?
I don't quite remember.
So it is not difficult to prove this. So we have three operators, A, B, and the commutator of A and B. Okay. The first thing you can examine is this function, e to the minus alpha A, B, e to the alpha A. Okay. Call this function g of alpha. G of 0, what is g of 0? This is 1, this is 1. These are operators. Huh? This is B. And if you compute the derivative of g of alpha with respect to alpha, when you make the derivative of this, you get minus AB. And when you make the derivative of this, you get BA. So this is minus e to the minus alpha A commutator B A e to the alpha A. Okay. Like alpha e to the alpha obviously commute because this is a function of this. So A, and so you get minus AB plus BA, and this is C. This is C, so this is minus e to the alpha A, C, e to the alpha A, but C commutes with A, so this is just minus C. So in the end, you get the derivative of G over alpha is minus C. So G of alpha, it is B minus alpha C. This is this expression. Okay. Now you compute the same way f of alpha. This is e to the minus alpha B, e to the minus alpha A, and the formula e to the alpha plus B plus alpha plus B plus alpha squared over 2C. make the same computation, and in the end you have proven the Baker-Campbell-Hausdorff formula, which is that formula. Because the derivative of this, you can prove that the derivative of this with respect to alpha, because of this formula, equals 0. So this means that f of 0 equal to f of 1, and this is the Baker-Campbell-Hausdorff formula. So do this as an exercise home. I will put this as an exercise in the week assignment sheet. So if you have in mind this formula, let us compute u of alpha, u of beta. This is a to the I alpha q. This is a formal computation. We use this formal computation to set up the commutation rules. So a to the I alpha q, a to the e beta p. This can be vectors. Alpha q can be alpha 1 q1. We are discussing indeed n-dimensional systems. So what is this? This is a to the I alpha q plus e beta p plus 1/2 of the commutator. The 1/2 is minus alpha beta minus e over 2 because the commutator has an e minus e over 2 alpha beta. Okay. And the reverted computation will give to us a to the I alpha q plus I beta p plus I over 2 alpha beta. In such a way that we are writing u alpha v beta equal v beta u alpha a to the minus I alpha beta. This is the Weyl representation of the commutation rules, of this Heisenberg commutation rule. U alpha v beta equal e to the minus I alpha beta u beta u alpha. And also, of course, u alpha u beta equals u alpha plus beta, and v alpha v beta equals v alpha plus beta. This is the system of commutation rules which translate under suitable hypothesis, by the way, which I don't spell now, but which are at the basis of the Otherstone theorem, translate the Heisenberg commutation rules into commutation rules of a group of unitaries. Okay? By the way, with this commutation rule here, you can write the commutation rule this way, this one, v beta u alpha v minus beta equal e to the I alpha beta u alpha. Okay, so this means if we translate using the a to the I beta p, a to the I alpha q, a to the minus I beta p equal to the a to the I alpha q plus beta. This is maybe easiest to remember. But also this formula tells you that q cannot be a bounded operator. If you take the infinitesimal generators of this formula, you get that a to the I beta p, q a to the minus I beta p equal q plus beta. So q is unitarily equivalent to the operator q plus beta. This means that the spectrum of q is the whole real line. It cannot be bounded because if it was bounded, the spectrum would be bounded by this norm. Okay. So now these are the algebraic rules fixing, giving an algebraic structure to the Weil algebra, which is generated by these operators. Okay. And now the second step will be to put a norm on it. So it is easy to say that these operators U have to be unitary. This is obvious because U of alpha, U of minus alpha equal 1, the identity in the algebra. Then, because of the spectral radius formula, you can show that this definition extends to the whole algebra. You can use this definition to produce a norm on the whole algebra and make this algebra a sister algebra like in our general scheme. Okay? This is a technical difficult step. I won't take it here. It will take hours to do it. But it exists a unique norm extending the obvious one to the whole linear combination of elements of this algebra. Okay? And now we come to our question. How many representations are there of this algebra? Okay? So the question is, we have constructed an algebra. The algebra is based on this commutational relation here. Now we look for representations, means we are, this is an element of the algebra. We want a pi of U of A representation of this element of the algebra by an operator, which I can write also this way. An operator in a Hilbert space. In principle, one can expect that there are infinitely many inequivalent representations to this algebraic rules, but the answer is that may be surprising. There exists only one up to unitary equivalence, regular, irreducible. That's why that's in this case we will get pure states. Isn't it? Irreducible representation of the Weil system. So we need to make precise what is the meaning of these words, regular and irreducible. First thing, regular. Regular means that the representative of U of alpha and the representative of U of beta have to be strongly continuous group of unitary operators. What does it mean, strongly continuous? Strongly continuous means a limit in the strong sense of a sequence of operators in the Hilbert space is a limit in which you compute the norm of your sequence. Let's say is a limit in which such an object goes to 0. In the strong sense means that you are considering the norm of sequence of vectors. Okay, so in our case, we get a group of operators. When t tends to 0, this has to tend to the identity. Okay, when applied to any vector in the Hilbert space, this means strong continuity. Okay, this has to go to 0. But if you compute this, this is u of t minus 1 psi. U is an unitary operator. Scalar product u of t minus 1 psi. This is the scalar product in the Hilbert space we are considering. Okay, so u is unitary. So what is this? U of psi, u psi, u psi plus psi psi minus twice the real part of psi u psi, u of t psi. So you see, because since this is unitary, this is twice the norm of psi squared, which is a number, minus twice the real part of psi ut psi. This identity means that strong continuity is equivalent to weak continuity. When you consider now the limit not of normal vectors, but of mean values, this is a property of the Hilbert space, in which strong and weak topology coincide. Okay? And this in turn means that you just have to ask for the following property. Psi u of t. Psi is Lebesgue measurable. It's a function which you can integrate. That's the hypothesis. Okay? Did I use any word which is not familiar to any of you? Every one of you knows what Lebesgue measurability is? Lebesgue integral. So this function has to be integrable with respect to the Lebesgue measure. And this is what will fail in the infinite dimensional case. Because as you probably know, the Lebesgue measure is simply dx. Okay? In the n-dimensional case, is the only translation invariant measure, complete Borel measure on the line or on the plane or in n-dimensional Euclidean manifold. When you want to extend this to the infinite dimensional case, you cannot do it. There exists no Lebesgue measure in the infinite dimensional case. So this hypothesis, which is crucial in proving the von Neumann theorem, the measurability of these expectation values, won't hold in the infinite dimensional case. And this is the reason why quantum field theory admit infinitely many inequivalent representation.
Do you mean integrability? Because this is much stronger a statement than measurability.
Measurability. So but this integrable, it is obvious because this is a unitary group. You see? It does mean that the integral converges of everything. The function is measurable. Then we will multiply it by a Gaussian, and this will make the integral converge. Just measurability. Okay. This is an equivalence of in Hilbert space. Measurability implies weak continuity implies strong continuity. Is there any comment? Okay, so this is the word regular. You ask the strong continuity of these operators. This is a fundamental notion in Hilbert space because you know that when you have an Hamiltonian in your quantum mechanical system and you want to construct the quantum evolution, you are going to write this thing. But to write this thing, you need the self-adjointness of the Hamiltonian operator, and this will imply, by another theorem by Stone, that this group is strongly continuous. So strong continuity is also at the basis of the requirements that you can solve for the evolution of your quantum mechanical system. So I'm asking something which is standard in quantum mechanics. This mathematical property of strong continuity is the same which allows to you to solve your Schrödinger equation. Okay? The second word you see here is irreducible. A representation is irreducible if the only subspaces of H which are invariant under the application of the representative of the algebra, the only invariant subspace is the vacuum, not the vacuum, the zero vector and the Hilbert space itself. This means irreducibility. Means that every vector in an irreducible representation is cyclic. While in the GNS construction, there is one vector which is cyclic. In an irreducible representation, every vector is cyclic. You see the difference? Okay. So under this hypothesis, we will prove that there exists only one representation in a Hilbert space of this relation, which is indeed the equivalent to the Schrödinger representation. Are there questions? Otherwise, I go and prove the theorem.
Oh, so when you mentioned a cyclic vector earlier, you meant cyclic as in group action, like?
Yes. Means that you have a vector, and then you have your operators P of A, which represent your algebra in the Hilbert space. You consider linear combination of all such vectors. You make the closure of this set, and this is the Hilbert space itself. This means irreducibility. So we will construct a particular vector now, which is called the Fock state. And this will completely characterize the representation of our algebra. So the first thing to do is to introduce the Weyl operators W, alpha, and beta. So W alpha beta is, let me put here these quotation marks. You can think of this. Okay. So let's compute what it is. W alpha beta, W gamma delta. This is, let's do the same formal computation we did before. So this is e to the I alpha plus gamma q plus e beta plus delta p and the commutators, e to the 1/2. The commutator of Q with P is I multiplied by minus alpha delta plus beta gamma.
Should that, you said plus?
Minus alpha delta, there is II, which makes a minus, and Q commutator P is I. You see here appearing the symplectic form in R2N. So this is e to the I. There is an I here. Over 2 alpha delta minus gamma beta. W of alpha plus gamma beta plus delta. In passing, I tell you, to some of you which might be interested, if you define the so-called Weil quantization by integrating the operators over test functions, and you compute the product, you call this W of F, and you compute W of F plus G equal, if you compose this thing, you get here the so-called Moyal product. And the deformation quantization starts here, but we don't enter in this direction. Okay? We are content with these algebraic relations, which are completely equivalent to the relation I wrote on the other blackboard. Okay? So, consider a strongly continuous, irreducible representation of these relationships, and define the operator P. Okay. Here the strong continuity enters because this function, as we said, is measurable, and we multiply it by this exponential. This integral converges, and this operator exists. Okay. This is the crucial ingredient of the proof of the theorem, because the property of this operator are, first thing, P is a self-adjoint operator. I should put a hat on it. This is because W equal to, because of its definition, W of minus alpha minus beta, and then you change the variables in this integral, and this is equals to itself. Okay? The second property, which is the most important, is that this is a projection operator. P squared equal P. Okay? This is just an integration. Let's do it. So what is it? P squared. p squared one over 4 pi squared e to the minus alpha square plus beta square plus gamma square plus delta square over 4 w alpha beta w gamma delta di alfa di beta di gamma di delta. Okay. Then we use the multiplication rule, this one. We are in the representation. Huh? Is equal 1 over 4 pi square e to the minus alpha square plus beta square plus gamma square plus delta square over 4 w of alpha plus gamma beta plus delta. Here the group structure enter here at this level e to the minus e over 2 alpha delta minus gamma beta okay. Now we change the variables. We call alpha plus gamma equal to u, beta plus delta equal to v. This form is invariant under this change of variables, this symplectic form. And then, okay, let's go one step forward. 1 over 4 pi square. So I call gamma u minus alpha beta v minus delta delta v minus beta in such a way that this is going to be w of u and v. And then we will add here e to the minus alpha square plus beta square. Gamma is u minus alpha, so I get a 2 here, plus u square minus 2u alpha. And delta is v minus beta, I get a 2 here, plus v square minus 2v beta over 4. And the phase, which is important, of course. Without it, nothing would be working. The alpha, the beta, du, dv. Okay, so now if you complete the squares here, you will see that, so let's do, for instance, I have square root to alpha, okay, plus here I get minus, let's say, because I have minus u minus, here I have alpha u, and here I have gamma v. You can see that if you do this change of variables, alpha delta minus gamma beta equals alpha v minus alpha beta minus gamma u minus plus alpha beta. So this is alpha v minus gamma u. Yes?
What you wrote in the integral there was alpha u minus gamma v.
Excuse me?
You wrote something different in the integral there.
Here, alpha u minus gamma v.
V and U.
But what you wrote there is alpha v minus gamma u.
Okay, alpha, because I'm wrong. Alpha v minus gamma u. So you complete, but you're going to complete the square here, and you get here u minus v square over square root of 2, the whole square. Then you change this variable to what you call, let's say, x. Then you have a Gaussian integral times p itself. And the Gaussian integral, because of this 1 over 2 pi, gives 1. This is going to be 1 over 2 pi e to the minus u square plus v square over 4 w of u v du dv equal p. Okay. Work out this step home. Is just a change of variable, nothing more difficult than that. So another exercise, home, compute this. And prove that this is equal to e to the minus alpha square plus beta square over 4 p. So this is the central object of the proof of von Neumann, indeed. It is a projector, and because of the cyclicity, the irreducibility of the representation, it is a one-dimensional projector. This follows from the irreducibility of the representation. What does it mean? It means that there exists one vector in your Hilbert space which satisfies this equation. Okay? Only one vector up to a phase. So we can compute the expectation value because of this rule here that you have to prove as an exercise on. We can now compute the expectation value of W in this vector, which, as every other vector in this representation, is cyclic. So I insert the projector operators. Then I use the self-adjointness of the projector operator. And then I use this property here. And I get e to the minus alpha square plus beta square over 4. This is the expectation value of the while operator in this vector. So if you now go back to the proof of the GNS theorem, you will see that this representation, because of the structure of the GNS theorem, is equivalent to the GNS representation in which you give these expectation values to W alpha beta. Okay? And because, again, of the GNS theorem, since such vector, this operator exists in any irreducible representation which is strongly continuous. Give yourself an irreducible representation, which is strongly continuous. Construct this operator, find the vector which satisfies this equation, and this is your Fock state vector. Every other representation which has this property of irreducibility and strong continuity has such a vector. Because of the GNS theorem, they are all equivalent. And this is the end of the proof. Okay, why do we call this vector the Fock state vector now? The reason is very simple.
And this vector has to be not the zero vector, right?
It has to be non-zero. You can prove that it is non-zero, again, because of this property. There is one step to be complete, as you say. You should say that this operator can be vanishing, can be zero. Why it is not zero? Because if you insert this property here, you will see that if it is zero, I mean, this would imply that the Fourier transform of all these operators is zero. And because this is not possible unless it is a trivial representation, this operator is not zero because of Fourier. So there is one step to be complete, as you say. You should be sure that this is not a zero operator. And this comes out, again, from the Weil relation. Because of this phase, you input here this, always with this definition. You put here, let's say, how do you proceed? You put here, you compute this, W of minus alpha minus beta, P, W of alpha beta. Because of the commutation rules, this makes this phase enter in the integral. So it would imply that this Fourier transform vanishes, W. And this is, of course, not possible by hypothesis because you have a representation. Okay. So I wanted to justify the name Fock state. So we have seen that the representation, the unique representation of the Weil algebra is characterized by this property. Okay. The expectation values of the Weil operator are these Gaussians. If you compute now the expectation value of U alpha B beta, which by the theorem we have just proven is the expectation value in the Fock state of the representative of U alpha V beta, because of the relation between V alpha and V beta, which I've written somewhere, but I don't see anymore. Let's compute it again. W alpha beta is e to the e alpha q plus e beta p, and U alpha V beta is e to the e alpha q e to the e beta p equal to the e alpha q plus e beta p minus I over 2 alpha beta. So U alpha V beta equals W alpha beta e to the minus e over 2 alpha beta. So the expectation value of this is the exponential of minus alpha square plus beta square over 4 e to the minus e over 2 alpha beta. So if you now compute this thing, you see that this vanishes. Apply this operator to this exponential. And then if you use this thing on this expression, and you use the commutation rule between Q and V of B, you see that this is equivalent to the condition Q plus EP applied to the Fock state equals 0. So the Fock state is destroyed by this operator. The Fock representation is the unique representation of the canonical commutation rules. We can say it this way. To pass from here to here, you have to commute Q and V of beta. And this will be Q minus beta, V of B. So when you make the derivative of U, you take Q, and then you have to pass this vector here. There is a plus beta here, minus beta. This gives Q plus EP. This is Q plus B plus EP. When you commute with this, you get this. And because of the cyclicity of the vacuum, the irreducibility of every representation, since you have proven that psi 0, U alpha, V beta, Q plus EP applied to psi 0 is 0, this implies that this vector is 0. So that's the reason of the Fock state for this vector. It is destroyed by the destruction operator. And this is a unique representation of the CCR when you have a finite dimensional system. Okay? So summarizing, if you assume irreducibility and regularity of your representation, you can construct in any such representation a projector. And this projector gives to you the Fock state. And this construction is unique. Okay? It will not work in infinitely many dimensions because the representations are not regular anymore. So there will be uncountably many inequivalent representations of the same algebra when this algebra becomes infinite dimensional. And that's the crucial difference from quantum mechanics to quantum field theory, which is not at all special for curved spacetime. It is also this way in flat spacetime. So we will study for one lecture or two maybe, now quantum field theory in flat spacetime to put in evidence the structure of the theory. The last thing I want to say about this is that since we said that there is a unique representation, we can use the Schrödinger representation. In the Schrödinger representation, in the end, just to end with this, let me tell you the explicit expression of the Schrödinger representation. In the Schrödinger representation, U of A is represented by C of x e to the minus E alpha x C of x, and V of B, C of x is CB of x. This is psi of x plus beta. These are the representative of our groups in the Hilbert space of the function which are integrable with respect to the Lebesgue measure. So in the homework you will show that this is a representation, this is obvious, but that this representation is irreducible. Since it is irreducible, it is the unique representation of the canonical commutation relation up to unitary equivalence. Okay. So proof in the week assignment of this week, the irreducibility of this. I will send you a file with all the definition and everything. Once you have proven the irreducibility, you are sure that this is the representation of the canonical commutation relation for an n-dimensional system. Other questions?
Just to check, strictly speaking, P and Q are not defined in this representation.
Excuse me?
Or are they? Yeah. Strictly speaking, are P and Q defined in this Fock representation that we were talking about just before?
Here, yeah.
We constructed a representation of the Weil algebra.
No, we were representing it, and since this group of operators are strongly continuous, you can take the generators, and they are essentially self-adjoint because of the strong continuity of the group. So there is one operator corresponding to the group which is essentially self-adjoint.
Okay, so all the operators of the representation are bounded, but not
No.
in the GNS, when I do.
These operators are bounded, yes. These are unitary operators, as you see.
Yeah.
But when you take the generators of such operators, they are not.
Right.
They do not belong to the algebra either. You need to do something to construct.
That's
Okay. Yes.
You mentioned, excuse me, you mentioned the Weil algebra works for any finite number of dimensions, right?
Yes.
So that would be.
But you can construct such an algebra also in the infinite dimensional case. The difference is that will be no unique representation.
But so you do that by considering like up to n q's and p's or something like that.
Excuse me?
How do we represent how do we show these n? How do we distinguish between the different particles in this Weil algebra you set up?
At the moment, there are n particles which are distinguishable. There is not no symmetrization for the moment.
So, for example, how do you measure the momentum of particle 1?
You call it P1 and you measure P1.
No. Perhaps I'm not being very clear.
Probably I don't understand your question. Maybe we can discuss later.
All right.
Okay. Do we want to make a 5-minute break, or we go on and I'll tell you about retarded and advanced solution of the Klein-Gordon equation? 5-minute break, maybe. Okay. So we can discuss now if you want.
What I meant is, what you were doing in the whole derivation of the Weil algebra, there's just one p and one q, right?
For NP and Q. Sorry? I mean, you can think of this as vectors.
Oh.
But I can construct an equivalent representation in which the symmetrization appears explicitly. But in this construction, you don't see it.
Yeah.
I don't know if the person.
Yeah, I think.
Yeah. I think so. I'm not sure. Yes. How about it? I don't know. Because you cannot be here?
You mean the structure? Yes.
Well, you come from London.
Yes.
That's what I'm understood.
You are bankrupt.
Yeah, that's strong. That's strong.
You cannot be here every day?
If I proceed, my supervisor, he's available.
I see.
So these are.
Unfortunately, I'm here just for 1 month and a half. So if you want to discuss also, better you come. But you do.
But this Wednesday is probably. Wednesday is
Maybe it's
Wednesday you will be canonical quantization.
I don't know. I'm stuck now, and then I go on up to the quantum field conquer space. I'm not sure I will finish on Wednesday, of course.
So today.
Now I do the first step today
Which will be.
to build the scalar product and all these things in a logical way. Then you are familiar already with these things.
Yeah.
But I mean, I'm complementing information you already have.
Oui. Ouais. Hier, je ne sais pas mauvais non plus, mais... Non, il y avait la place. Bah, moi aussi, je parle de famille ou amis, c'est ce genre de méthode. Ouais, déjà, c'est dans ces agissements, tu tires une base, après, c'est rapidement, pire que d'autres, une demi-part. Et puis les maisons en elles-mêmes, donc là, c'était la maison la plus c'était clair, grosse physique. Quasiment un deuxième de maison, c'est un peu des détails en plus en bas, on a pas l'impression c'était soir. Dans la partie bureau, le sol arrive de certains. Mais je sais pas très bien, tu vois, dans ces maisons, il y a un truc, c'est comme si les gens décidaient de recommencer toute leur vie à zéro. Tu vois, je sais que tout est préfabriqué, les tableaux, le choix des meubles, les tableaux, rien de personnel. La difficulté vient de le choix des meubles déprimants, mais tous les tableaux, même justement, c'est des choix, des vrais choix, mais vraiment l'impression que tu as tout à ton équipe qui a été acheté en un clic sur Amazon. Le personnel, c'était un peu des la décoration.
Excuse me, could you please explain again the strong continuity and could you please explain again the strong continuity and the weak continuity?
Yeah.
I didn't quite hear.
Maybe I explain to you personally at the end of the lecture, because now I'm starting something different. If you have 5 minutes, I will explain to you that.
Tous, ouais. Tout est super moderne. Ouais. Je non mais nous, même, la chambre, c'est un peu ça. Dans une chambre. Nous, on a 2 ans, ça rame, ça, donc c'est un peu à l'image, toute la maison à l'image de ça. Le miroir parfait, le tableau qui dit chaleur.
Some more,
the solution is right.
Live your life. Ok. Tu l'achètes où cette... Hein?
Matteo is coming back?
Yeah, I think so.
Wait.
So you can probably go ahead though. Yeah.
Okay. So now we are going to do something which is really elementary. I make. Now we go to system having an infinite number of dimensions. So we are considering fields. And in particular, we are considering Klein-Gordon fields. And we are considering classical Klein-Gordon fields on the Minkowski spacetime. The Minkowski spacetime R4 is endowed with the metric eta nu, which has this signature in my conventions. Scalar products okay, so this is okay. And the elementary problem I would like to solve or remind to you how do you solve such a problem is the Cauchy problem for a Klein-Gordon field. Let me remind you that the notion of field was invented by Faraday when he was studying magnetic fields, and yet clear that a field modifies the space in which the field lives, and a space in which there is a field is no more empty. This is already in the word of Faraday. And so a field is used, as you all know, but let me tell you, since this is a course, to describe something which is otherwise impossible in a relativistic context. It is impossible to talk about action at a distance. So the interaction is mediated by fields. From the mathematical viewpoint, if we consider such simple equation, the first thing we would like to know is how do we solve the initial value problem. Or also known as the Cauchy problem. This is the standard problem, standard way of thinking physical problems. You know the position and the velocity of your system at an initial instant, and the equation of motion provides for you the time evolution of the system. Okay, so you give yourself this function at an initial time, the time derivatives of this function at t equals 0, these are your initial conditions, and you want to know the solution of this problem. Every one of you knows how to solve this Cauchy problem? I think yes. All right. You go by Fourier transforming. Fourier transform solves completely this problem. You know how you proceed. Take this equation and Fourier transform it. So Fourier transformation, let's define it. If I have a function in R4, its Fourier transform is the thing where here I input this Lorentz invariant scalar product. Okay, this is by definition the Fourier transform, and if there are mathematical conditions under which you can invert this transform under very different hypotheses, you can reconstruct the function f of x by inversion of the Fourier transform. The advantage of Fourier transform, of course, in solving this kind of equations is that a partial differential equation is transformed into an algebraic equation, because if you put here the D'Alembert operator, you integrate by part, and then the derivative of this is just minus k square, where square is the square Lorentzian square. So the equation, Klein-Gordon equation, in Fourier space is written minus k squared plus m squared phi of k equals 0. K squared, once more, is k0 squared minus k squared. So you have changed partial differential equation into an algebraic equation. This, of course, is solved in a space of distributions. Means that the solution of this equation is phi of k equal delta of k squared minus m squared times an arbitrary function psi of k. Okay. So you see that the spectrum, let's say, of this phi is concentrated on the mass shell, which has two components. This is delta of k squared minus m squared times theta of k0, which is Lorentz invariant. This is in the future. Theta is a Heaviside function. And this is theta delta of k squared minus m squared times theta of minus k0. Okay? Now you invert this Fourier transform and you write your solution this way. Let me write it. Because this is, I'm doing this, you know very well these things, but this is at the basis of everything. That's why I'm going through these steps. When you invert your Fourier transform, you get two components, let's say. One is a to the minus ekx theta of k0 delta of k squared minus n squared times a function c1 plus the component on the backward mass shell times an arbitrary function c2. These are functions of three. By the way, because of this, so if you make the one integration, here you got e to the minus omega t plus ckx d3k over omega, 2 omega, okay, 2 omega, c1 of k, omega is square root of k squared plus m squared plus e to the I omega t, the other component, plus ckx d3k over 2 omega c2 of k. This is the solution of your problem in general. Now you have to input your initial condition. Okay? Is every one of you very familiar with this or not? Tell me the situation. Is there anyone in difficulty? No. So I skip the steps. You do the integration and you impose the initial condition by Fourier transforming those initial conditions. You arrive to define, you are led to define an invariant function, delta of x, d of x. This is already here, I'm not inventing anything. It is the so-called Pauli-Jordan function, which is the Fourier anti-transform of this distribution when you impose your initial condition, and you will see that the solution phi of x satisfying those initial conditions is written in terms of this Jordan-Pauli function this way.
Excuse me? What's an epsilon of k0?
Epsilon is the sign function. It is -1 if k0 is negative and +1 if k0 is positive. Okay. So this special function, which you will compute in the week assignment, as a reminder, because I'm sure you already done this exercise, it is used to solve the Cauchy problem. We can, by the way, verify a posteriori this formula, because if you look at this invariant function d of x, first thing you see that it is antisymmetric. Second, you see that it satisfies this condition and this condition.
Oh, so the Pauli-Jordan function takes it's over R4?
Yes.
Yeah.
It's not a function, by the way, it's a distribution.
Yeah.
You see here I'm multiplying distributions. There's no problem in doing this because the epsilon distribution has a singularity here, while the delta function have singularities there. So you can multiply them safely because you are not superposing singularities. Otherwise, when you know this is the problem of quantum field theory, and I will prove a general theorem that this is an avoidable feature of quantum field theory. Fields are distributions. We are talking here about classical fields, but the quantum fields are distribution. And when you want to multiply them, you get into difficulties because distributions cannot multiply, cannot be multiplied between them. Here, I have no difficulty in multiplying such singular function because their singular support are disjoint. This is the first thing. If you look at this initial condition for the Pauli-Jordan function, and you apply those initial conditions here, you see when you put 0 here, this integral disappears. You put 0 here, this integral is the delta function times phi, so it reproduces the initial condition. And when you make the derivative, you have the opposite here. Yes?
Are the singularities only disjoint when n is non-zero?
Excuse me?
What happens when n equals 0?
When n equals 0, you have indeed an arbitrariness here. When n equals 0, there is an arbitrariness here, and in multiplying those distributions, you can always adjoin. There is an indeterminacy here, which you can call a renormalization. So you have to choose the coefficient of this term you can add when you multiply this distribution when m is 0. There is an ambiguity here. So the Pauli-Jordan function d of x is used to solve the initial problem, the initial value problem. And by the way, the Pauli-Jordan function is the unique solution of this Cauchy problem here. And that's why once you have solved this problem with unique solution, apart from the normalization, no, this is normalized by this condition, is the Pauli-Jordan function. You can solve any initial value problem as convolutions of the Pauli-Jordan function and this time derivative with the initial data.
So
Okay.
you're just talking about the green function for the problem.
Excuse me?
That's also called the green function, right? Or is it different?
This is not really a green function. What I would call a green function, and this is the second step, is a solution of this equation.
Okay.
This solves the homogeneous equation. A green function solves the inhomogeneous equation with the source delta here. And by the way, there are people calling also this a green function or a propagator. Indeed, it is used in this formula as a propagator that propagates the initial data into a global solution. But it is normal to call a green function a solution of this equation. So this was the first statement. And then we will have to deal for a certain time with this function now. I will describe certain properties. This is for sure very well known to all of you. Now I will go a few steps forward, describing other properties of this function that may be not so well known. Okay, so but in the end, let me tell you the story in advance. Now we have constructed an antisymmetric function. In a way, the story will be this. We will construct some sort of Poisson brackets for fields, invariant Poisson bracket for fields, in terms of this function, this Pauli-Jordan function. You see, this is a Poisson algebra. And the commutator, you for sure already know what is the answer. The answer will be, put an I here. This will be the commutational relation. This is a classical algebra. This is a quantum field algebra. And it has acquired an I here. And the problem of representing the algebra, I will reduce this problem in finding a splitting of this commutator in this way. This is true in flat space, in curved space, in all the examples. And this object will encode the representation. This will be the leitmotif of the lectures I will going to do this week and maybe part of next week. But first, we have to consider another kind of splitting. The point will be how to construct this object, of course. In concrete examples, you want a procedure to do it. And this is already, in a way, encoded in this function, the way you should do it. Okay, this is the synopsis of what will follow. But now, let me just, as we were starting to say, consider now not the homogeneous Klein-Gordon equation, but the inhomogeneous one. Okay. Once more, you go by Fourier transforming. The Fourier transform of the delta function is 1. So G of k. I'm telling things that you all know very well, so I'm a little bit maybe fast. So that G of k is minus 1 over k0 square minus k square minus m square. Of course, so I would like to define the inverse g of x as minus 1 over 2 pi to the 4, the integral e to the minus ekx d for k k0 square minus k square minus n square. This integral is ill-defined, of course, because we step into a singularity while integrating over k0. You see, the denominator has zeros, poles, at these values of k0. So when you integrate over k0, this integral, you step into these poles. And as you know, according to the way you go around such poles, you define one on another green function. The two prescriptions which are relevant for us will be put the poles here or put the poles here. This means consider shift in the complex k0 plane, in which you put here k0 plus or minus I epsilon square. Now you don't have any more singularities on your integration cycle. And if you choose the plus sign here, you get what is called the retarded green function. And if you put the minus sign here, you get what is called the advanced green function. Is every one of you familiar with these things? Okay. So this means that in one case, this is your integration cycle. In the other case, this is the advanced integration cycle. This is the retarded integration cycle. In one case, when x0 is positive, you can close the integration path in the lower complex plane. In the other case, when x0 is negative, you can close in the upper complex plane in such a way that the advanced support is for x0 negative, and this is 0 otherwise, and the retarded support is for x0 positive. But the thing that is important for us so let's compute this difference. G retarded x minus G advanced x. You know the Sokotzy formula? That tells you that 1 over x plus I epsilon minus 1 over x minus I epsilon is minus 2pi delta of x in the distribution sense. So let us use this formula to compute this difference without doing any computation. Without really doing this integral. So here I have minus 1 over 2 pi 4 e to the minus I kx 1 over k0 square minus k square minus n square plus e epsilon k0 epsilon. This first epsilon is the sign function. This second epsilon is the epsilon entering there. This unfortunate notation, this epsilon k0 is minus 1 plus 1. You see, it depends on the sign of k0. I can put it also k0 simply here. but K0 can become large. It's the sign of K0. Minus 1 over K squared minus K squared minus M squared minus I sine K0 epsilon. Now I use this Sokotzi formula. It becomes I over 2 pi cube e to the minus a kx sine of K0 delta of K squared minus M squared, and this is just the Pauli-Jordan function. So this formula is of fundamental importance. The Pauli-Jordan function is the difference of the retarded propagator minus the advanced propagator What is the interpretation of this formula? Look at this invariant function d of x. D of x, the support of d of x is concentrated in the cone. This is the light cone, x squared equals 0. This is x squared bigger than 0, x0 bigger than 0. And this is square greater than 0, x0 less than 0. Okay? And d of x vanishes here. We will come back on this point. Of course, you know already. So this splitting consists in multiplying the Pauli-Jordan function by the characteristic function of x0. Of course, this notion is invariant, Lorentz invariant on the cones. Of course, it's not Lorentz invariant here, but it's Lorentz invariant here and here. It leaves invariant the inside of the forward cone and the inside of the past cone. So, to get the advanced and retard propagator, we are just splitting the commutator into two parts in X space. Okay? This is we can call it indeed, the retarded and advanced Green function can be called the retarded and the advanced commutator, because this in the end will be the commutator of our theory. Okay? So this is a formula that now we are going to use to set up the so-called Klein-Gordon product. Okay, are there questions on this?
Can you just explain that picture again that you drew?
Excuse me?
Can you just explain the picture that you drew? And what happened?
Once more.
Yes.
This is the Minkowski spacetime, R4. Okay? This is the light cone in Minkowski spacetime. These are the events such that x squared is positive. These are the events which are time-like separated with respect to the origin. Okay? These are the events on which x squared is 0. They are separated by light-like intervals with respect to the origin. And these events are space-like. Here, x squared, this is x, is negative. Okay? The Pauli-Jordan function is 0 here. This is, I will prove this fact. You probably already know it. I'll come back on this fact because this expresses local commutativity of quantum fields. But this is 0 here. For the moment, take it for granted. So how do you get the advanced and retard propagators? you split. So the Pauli-Jordan function is non-zero inside here. If you multiply the Pauli-Jordan function by theta of x0, means the function characteristic function of x0, you are just keeping this part of the Pauli-Jordan function. And this is going to be the retarded propagator. The retarded propagator is theta times the Pauli-Jordan function. While if you multiply by x0 theta of minus x0, you are going to keep only this part, and this is the advanced propagator, minus the advanced propagator. In such a way that their difference is the Pauli-Jordan function. Okay? This is very important for what follows. I start explaining this, and then maybe we stop for today. So if you now consider the Pauli-Jordan function, which, as I said, is the difference of the retarded propagator minus the advanced propagator. We know that the Pauli-Jordan function solves the homogeneous Klein-Gordon equation. Okay? So if you give yourself a function, f, any function, this is F4, give yourself a function whose support is here, let's say, and you can build the convolution of this function with your Pauli-Jordan function. This is the convolution product. You integrate, this integral converges. You can call this thing df. It is obvious that df solves the Klein-Gordon equation. You apply here the Klein-Gordon operator with respect to the x variables. You apply on this function. This solves this going to be 0 convoluted by f of y, and this is 0. Okay, so this is nothing very serious. What is important is that every solution of the Klein-Gordon equation can be written this way. Before we saw one possible use of the Pauli-Jordan function was to solve the initial value problem here. Now I'm telling, so you see here the solution is parameterized in terms of functions which are a function just of the space variables. Two functions of the space variable. Here I have one function of the space-time variables. But what I'm telling now is that every solution of the Klein-Gordon equation can be written this way. If you have a solution with initial data which are a compact support, you can always find a function here, f, in such a way that you compute the convolution between the Pauli-Jordan function and this function f, and this is your solution. So it's another way of writing the solution, always in terms of the Pauli-Jordan function, now as a space-time average. You see? And how do we prove this? To prove this property, it enters in a crucial way this identity. Let me just start with this thing, and then we will give the proof next week. This step is important because it is in this way that you are going to understand why this sort of the so-called Klein-Gordon product that you use in quantum field theory in curved space-time, where does it come from? It comes from here. Okay? So let me just tell you one thing more, and then we will continue on Wednesday. What is the use of the retarded and the advanced propagators, since they solve this equation? They both solve this equation, but they do solve this equation in different ways. So if you want to solve this problem now, is the Klein-Gordon equation with a source where the source is a function of compact support. Suppose this is F4. Give yourself a function here. Doesn't matter that this is at the origin. This is the support of the function f. If you write, for instance, this convolution, when you apply the Klein-Gordon operator here in the x variable, this is going to be delta of x minus y f of y equal f of x. So I've solved this problem. But how did I solve it? The support of this function here, called phi, this phi here, has support here. This is the unique solution of this problem, whose support is in the future shadow of the support of the initial function. The support of phi is the support of f plus the future cone. Means draw all the cones whose tip is in the support of f, and you get this domain. If you do the other thing, if you solve again, but the advanced solution, this is, I call this P2. This is, of course, 0 for the same reason, but now Phi2 has support in the backward tube. This is Phi1. Solve this equation with support in the causal future of the region F. This is Phi2. And obviously, the difference Phi1 minus Phi2, which has support here, solves the Klein-Gordon equation, the homogeneous one. And the theorem I want to prove next week, which is founding the Klein-Gordon symplectic form, is that any solution having compact initial data can be written like this. So if you give yourself a solution of the Klein-Gordon equation whose initial data are of compact support, you can always write this. There exists a function f in such a way that the solution is written as so this psi. The task will be to found this function here in such a way that this solution is written as the convolution of the Pauli-Jordan function with this space-time function. This will settle the Peyerl's bracket, and then we will move to the commutation relation. Okay? That's enough for today.
Sorry, I know this isn't all that important in the grand scheme of things, but G retarded, G advanced, which of them has the theta minus x0?
Excuse me?
Should G advanced be minus theta minus x0?
So let's verify if I write this way, but then this is G retarded minus G advanced. G advanced is minus theta minus x0.
Alright, it's just you can't really
It's a
see the
definition.
minus in where you wrote it there.
Minus, yes. Okay, are there other questions? So next Wednesday I will prove this theorem. Any solution is written like this, and this will give the Peierls bracket.
I mean, back to the previous section of the course when we were talking about the Weil algebra, the whole project started from choosing canonical coordinates on phase space. Is there a way to make sense of this construction in a purely geometric way that doesn't involve picking out P and Q as specific representatives of canonical coordinates? Does the question even make sense?
What do you mean exactly? If there are always Lagrangian coordinates?
So we started from phase space with fixed canonical coordinates P and Q on phase space, and then constructed the Weil algebra.
This is the Weil algebra.
Quantized. Is there a meaning for quantization in that sense that would not depend on picking coordinates? In phase space?
It always depends on the existence of a symplectic form, generic. If you give yourself a symplectic form, you have a unique representation of the corresponding Weil system. The Weil system, if you think of W is completely characterizing the Weil system, we get the standard symplectic form there. Then you can put there any symplectic form you like, and the theorem goes through the same way. I'm not sure I'm answering your question.
So to construct W, we constructed first U and V, which involved P and Q were...
But this I did it to motivate the commutation relation, but the starting point are the Weil relation. I forget about Q and P and think of U of A, V of beta, U of alpha. This was just to go there, but then the starting point are the unitaries describing these things and the symplectic form. For any symplectic form, you have this Weil system. Also in the infinite dimensional case, by the way. But I'm not sure I'm answering.
Yeah, so if P and Q and U and V dependent on choosing coordinates on phase space, you're saying the Weil algebra doesn't depend on choosing coordinates on phase space.
It depends on an abstract symplectic form, yes.
Okay, thank you.
Is there a reference for this lecture? Or do you have a...
This is from any standard textbook in quantum, in classical field theory. I mean, this theorem I did not prove yet. I took it in the book by Wald. This part here, and that one is from Peskin and Schroeder. Okay. And the proof of the Weil system once more in the book of Stroki, I quoted last week, in the book of Bogolyubov, Logunov, and Todorov, in which there is a discussion also of the infinite dimensional case. Okay. So see you on Wednesday.